the first activity today, I will invite our first guest speaker, Mr. Othman Younus, for Northumbria University. Please come here.
Good morning, everyone. Just to familiarize myself. Good morning, everyone. First of all, I would like to thank the organizer, everyone, whoever arranged, invited us, organized the event. It was the first time for me in this such a lovely country. I think for the first time for me from a Latin American country as well. So I came from the Far East way. So my name is Othman Younus. I'm originally from Iraq, is a Middle Eastern country, so it's very far from this area. Yeah. So a brief introduction about myself. I did studied in Northumbria University. I migrated to and started my master, doing my master with Professor Fari, who is presented here. And I did my PhD as a part of the Optical Communication Research Group led by Professor Fari again, you can see it, in Northumbria University. And I'm currently a member of different laboratory, basically active member in ECRN is the one that's been presented by Professor Stan yesterday, as well as led by Stan and Fari as well. And yeah, today is I will basically go through a brief introduction, or let's say a bit of thorough about the optical camera communication. So I will have a gradual complexity level. So sorry for those who are expert in the field. So we'll start with the beginning introduction about the topic and going forward in that. So I hope you will enjoy it, and I will go again with the thing. So here is the content of my topic today. So it's just to introduce to basically, hopefully that most of you are familiar with the concept of VLC and the moving on in the concept of that optical camera that was. Even yesterday, we have a brief presentation from Vicente about that, and moving into some related project and overview of what we do, and then as a final comment on that. So I just start with maybe a simple slide and saying, why do I need a new wireless? As you know, when we do anything, any concept, anything, it's driven by a need of something, yes? Otherwise, there will be no need. So here is a simple of, maybe I want to engage with the audience and to get more people involved in that. And it says, why do I need a new wireless? I mean, what will it bring for me in principle? What will I get? You can see here is some people saying, it depends on the research you do. It's just the direction. I just put that forward to show, what is the benefit of doing that wireless, and why do we need that amount of scientists doing this research, and what is the significance of that research? So I'm just to get everyone engaged. Please, if you do have a smartphone, just scan that one or put this, and you can put a reason for that, and you will straight away, it will appear in the slides. So let's have an opinion of what do you think about the benefit of that? It's a bit of engaging. It will not take more than 3 minutes, 4 minutes. So
just comment.
Yes, maybe start with that.
Because we want more trouble.
Yes, yeah. Maybe we can start with you, Ijaz, yes?
Yeah, I mentioned we want more trouble. So we want more challenges.
More trouble, all right. That's a bit of this. Anyone have any say on that? We do a research on that. I mean, we have to be driven by something, yes? So why I'm doing that research, why I'm actually looking for a new wireless, what is the benefit of, I mean, yesterday I've seen some presentation saying that the driven is like, let's say, ultra low latency, for example, to get a low latency signal for a use of, I don't know. This, I guess no one is putting any comments. So once you scan that one, you can, whatever you comment, it will appear in here. So,
really?
Yes.
I really didn't. I was writing because we want more devices.
Strange.
Better quality of service.
Better quality of service. Anyone else? Maybe cybersecurity. Okay. Any other comments on why do we need actually wireless or a new wireless or a new technology? 6G, 5G, 3G coverage to cover more areas about internet. Okay. Application on demand, basically part of Internet of Things and so on. Okay, these all are actually right one. I'm not sure why we are not able to see that, but probably I will go forward with that and we can continue with this. So I just adapted some slides from concept that about Fari was developing, and with the help of actually AI, and it's like, okay, let's go through the revolution and what we have done as a human from an industrial revolution point of view, and moving forward to the invention of that concept of wireless. You can see here is moving from the first generation where people actually start to use machines in order, and power machine in order to basically achieve their need from a lot of basically industrial revolutions. You can see this is in the 70s, and moving forward in that, you can see that this is led to the mass production of electricity, the invention. When the electricity came, it changes the life of the human. And then the third revolution then coming from the IT and basically the concept of automation, where we start to use machines to do things for us. And then the last, basically what they called it and trying to categorize them, is the fourth generation, where the, as you say, the mention of the cyber and physical security and system and automation things, that is the 25th centuries they're presenting. This can include all of whatever we have talked about, from providing, then they say that different types of communication technology, cloud service. You talk about robotic, drones, virtual reality, wearable devices, smart environment. All of these can be a part of this current trend of whatever we have progress as a human, let's say, from a general point of view. So again, here we talk about what communication technology that have been currently. I mean, if you get an overview of what is the communication technology that we currently have, and let's say people are seeking in research, mainly, I just put forward one of the things is the CubeSat-based laser communication. I mean, the need for the space, you can, if you go now, a lot of research, a lot of areas that working on CubeSat. For example, a CubeSat is a concept of having a small satellite that to provide a coverage for basically a large area from the space, and that basically miniaturized satellites, a small size of satellite, and that actually to provide the low, basically a power efficient, low mass, and provide the speed with this. So one of the, now you will see a lot of communication based on that concept of having a CubeSat communication. Another concept that is emerging research now, you can see the quantum communication, but where we use the quantum mechanics instead of the classical physics rule in order to basically provide the communication. I mean, what does this offer to us? You know, mainly a lot of research works from a concept of security, which is like quantum key distribution. So where actually it has a basis of superposition, entanglement, potentially offer a high speed because it's a parallel processing is compared with the normal classic physics. So a lot of research also looking into the quantum communication and that concept of having this, and a lot of research, a lot of progress on that concept of communication. Again, the need for the communication for having an extended reality and virtual environment where you need actually access to a lot and high bandwidth, where people demand the need for that one. You can see that a lot nowadays in augmented reality, mixed reality, immersive reality, metaverse, all this under the single umbrella of that extended reality, basically where you have to augment virtual photos or virtual things with the real environment to provide a blended environment for the users in which they can benefit out of that. Moving forward, the Internet of Things, nano things, you can see that a lot of actually now also, I would say research going that direction, where you look into the nano things, for you have a, for example, nano sensor that can nodes, you know, can be, for example, monitoring environment. It can be like for drug delivery, where you want to target cells in the human, for example, in a nanoscale, so you can have, we seek that way of communication and look for that point of internet nano of things where you want to provide that communication to these nodes and cells in a different level. So this basically type of communication technology that actually we look into it and say, okay, this can be a beneficial, and that we can seek a need for this in order to provide coverage, for example, need for nano for basic drug, for a lot of examples, basically advancing the need of that communication technologies for a human. Okay, again, I will just go briefly about some of other technologies that is actually adding to something to this communication. And you have, if you look into research, you can say, okay, starting from intelligent reflective service, again, a new way of communication, of helping basically the data to be steered to a users, to have basically, again, controllable element where actually you depends on the phase and the user, and you can target the propagation of the light signal or the wireless signal towards a user, whether it's a RF domain or a light domain. Again, a blockchain technology is a different way of having spectrum sharing, for example, to provide service and quality of service to user along the way. You can see that with a lot of concept of 5G. Beamforming is almost the same as intelligent, with a different way of looking at it. Actually, is directing the narrow beam with a high gain to certain areas in order to provide that high quality of service, or let's say service on demand for users. You can see that from an RF point of view, as well as from a light point of view. Cell-free communication. Okay, you have, so we progress as okay, you used to have a base station where the data is sent to the central station. The central station will redirect that signal to a user. Cell-free is actually, regardless of having a base station as a principal one or a central one, you basically decentralize it, and you have a, regardless of this, you can communicate with each other. You can find a lot of now technologies like, for example, NFC or whatever. This can be a decentralized one because you don't need to access a main server for that or a main station for that. So this is actually a brief way of looking into this. I mean, this is just a general view on this. Okay, I'm trying to, okay, sorry. Okay, looking into going ahead of this, you have the research about that millimeter wave, and that you have the basically going into high frequency, several hundreds of meters. You can, this concept of being introduced with the part of 5G on beyond, let's say, for a lot of basically communication technology. You can see here's even a terahertz bandwidth is a tens of meters. You can see the way of you designing the antenna and having basically multiple sources to send the information with a high frequency. Again, this can be questionable to some level from a radiation point of view, of hazard point of view. Okay, so moving forward on that, I mean, that's, as we also are going into the same principle of that conference, basically this leads us to the need for optical wireless communication, and the concept that been actually most of attendees hopefully are familiar, and for those who are not familiar, we'll get to know more about it. And the concept of having visible light and infrared and ultraviolet, basically having access to the optical wireless visible and invisible band that been now looked at, and from the point of view of having this gathering, as well as to hopefully strengthen that field. Okay, the concept here is going from the, we have a lot of basically the visible light wavelength spectrum. You can see here, we try to actually exploit that spectrum and availability for that one for communication purpose, or having a hybrid system where actually you combine all together to provide an optical wireless communication system. Okay, okay, sorry. So moving forward for the light, okay, I'll try to summarize, okay, what kind of light sources, what kind of optical domain, and what we have done as a human so far from having a light source, and how do we actually use these as a source for information, delivering information as well as for lighting. So you can see here is a simple AI generated content of the light sources actually going from 80s and going forward in that, and we will actually look into them one by one in here. So starting from having a light as a source of heat, communication, being used significantly in the past, I would say, moving into I was looking in literature and having that in the 13 BC, where people were actually worshipping that sun and the light source, basically moving that. And you can see that as in the Egyptian culture, I guess Akhenaton is that one of in the museum. You can see here is the light where people actually worshipping the sun. Okay, moving forward in that one. So moving forward, having the candle, and again is 1800, you can see the light in candles and being used for communicating the information, where you can have a candle to lighting basically the way of communicating. Moving forward in the 18, where you can see here is the progress into advancing of actually manufacturing and progressing of having these light sources. You can see the first incandescent lights is T79. Moving forward in 1960, where the laser was introduced. Again, the progress led to having an LED with a different way of having LED light sources, where you can actually use this, which is the principle of having that optical wireless. We can, for the visible light domain, where you can switch this with a certain speed in order to deliver the data. You can see here's again, this is with a short period of time. You can see the progress in light sources is actually phenomenal, and you see that the invention, like for example, the incandescent, it was adopted in 1870. It was started to vanish and rely on the LED as a alternative way of basically lighting the environment, where you provide a much more different way of actually looking in the lighting point of view. Here is, I just provided some cities where they completely, and towns, adopted the LED as a light sources and abandoning the incandescent light weight. So you can see, okay, the first LED used in a vehicle, basically headlamp. The first city was lit entirely in Italy, one of the cities, here is it. You can see they moved to use the LED. So that's why actually one of the drivens for us to actually look into the visible light as a way of communication. Again, what does it offer us instead of RF? Probably most of us hopefully know about that. And for those who are beginner, again, it's just the multipath. Basically, the multipath is much reduces compared with RF because it's more directional. You don't need a bandwidth regulatory. So I think it's already been mentioned before some presenters. You can consider that to some level an energy efficient way, because you're blending the light as well as the communication for the same source. Again, from a concept of security, because it's a highly line of sight and you need directivity, therefore it can be considered an enhanced security offering. You can have a lot of concept of the spectrum availability, no electromagnetic, it offers to somehow, so you can see a lot of actually advantages for having the use of optical wireless instead of the RF, or basically as a complementary technology to add that on top. I mean, these are one of the main guidance and driven unit of why are we actually looking into this research. Yes. We will actually question this at some point, and we'll come back and say, okay, we'll do that and improve that and look into each individual unit. But here you go, from a spectrum point of view, you can have access to 400 terahertz, like to 800, 400 to 800, if you use that available of that spectrum as compared with an RF. So now this, with the progress of Internet of Things, all of this technology, I mean, we look for alternative way of looking into communication to provide a way and facilitate our actually way of looking into things. Okay, here you go. Is a way of actually one of these advances of the LED and manufacturing. You can see that blue LED where light is actually, if you look to the wavelength and you have a certain beam width, and that actually the pulse of that light is coming out of this, and this is, you can offer basically a different wavelength of communication. You can, this is a simple way of looking into visible light, for example, moving into having the concept of RGB, the different way of actually having a light sources with a 3-color, and this is again the bandwidth and the spectrum basically that allows us to utilize that spectrum for that. So again, this is the way of looking into the spectrum and looking for the communication point of view. I'll just again move forward with this. I think these are sort of more introductory into this. Again, for the LED, the user, you can see it offers a high luminosity. You can see this is basically lifetime. It offered much longer lifetime in terms of compared with the different type of these light sources. I mean, you can see the concept of having LED to provide basically low energy consumption, reduce carbon emissions, and basically to be utilized as a in more often in our day-to-day lighting systems. So here is again just from a marketing point of view, so you can see the market expectation is growing rapidly for the use of this LED. So now if we look into this LED more deeply into, okay, what can we gain out of this? I mean, looking into sending this data, how fast can we switch these LEDs in order to transmit our data? I mean, is that possible? How fast is that can go? Then this give us a little bit of more knowledge about this, of having this. And basically these light sources were the bottleneck of having a communication high bandwidth for the optical wireless communication in general. Yes. Again, I'll just list this very fast. Again, here you go. Different light sources having an OLED, for example, 1 meg, less than 1 meg. Okay, moving into a blue LED concept of being invented recently. It's a Japanese scientist and he got Nobel Prize for the invention, 2014. Again, that offers a few megahertz bandwidth for the transmission. Different light source RGB concept offer like a bandwidth of up to 20 meg. You have a micro LED where it can a smaller size but higher bandwidth. The way of looking into actually providing and the semiconductor design itself, you can have a higher bandwidth, relatively higher bandwidth as compared with the other previous one. And again, the white LED and the blue phosphorus one, and you can offer over 100 meg. These are reported already and been invented and it's already existing in the market. Okay, this is from a transmitter point of view. Now, to more indulge in that and getting more in depth. So we have this information being transmitted. Now we're looking for the receiver point of view. Okay, so as a basics receiver that been used in literature and the semiconductor design, we have maybe, I could say 3 main types that we've been used to receive that signal. From a pin diode point of view, avalanche photodiode that offers a higher bandwidth but a higher sensitivity. And the concept of having multiple pin diode that is set in array, and that to receive in actually presented by an image sensor that can be commonly referred as camera basically. And that another way of you having these arrays of photo pin diode that is being structured together to capture the light within a certain speed, and therefore allowing the receiver to capture the signal. So these are the main ones. So now we are going more into these receivers and looking into more in depth in the camera, because this is what main topic for today. Okay, so basically why I'm using camera now is moving from the concept. We moved actually from concept of different communication towards the optical wireless. Then we move into the light sources and moving into the receiver. And now we are looking into the optical camera as a receiver for us. So use of camera, a lot of people been used. I mean, yesterday we heard 2 presentations from Vicente again about having camera and camera communication and the need for the camera communication. Now we will go a little bit in depth into that. So what does it offer us? A massive MIMO light source. I mean, to give an idea of this, I mean, that was suggested. We were walking with Pari yesterday, and and we were passing by a mall in here, yeah? Probably the people in here more aware of this mall, yeah? Fragarago. I'm sorry for my Spanish accent there because I don't know how to pronounce it. Yeah, you can see here the concept of multiple light source set together each of them can be treated an individual light source that you can actually modulate, send the data and receive that and offer that spatial modulation, different spatial wavelength. You can see different color, and these can be actually utilized for a certain communication schemes. You can actually use these for some certain cause or some certain application. This is one of the main triggers for using cameras. Okay, that can offer massive memory. This cannot be offered by a simple single photodiode. Again, moving forward from that concept to a concept of mobility, cameras actually now having a handheld mobile phone that can have a camera that actually provide you with a mobility feature. I'm sure everyone almost have a single or more than one single camera that have actually offered that feasibility for the use. And again, from a concept of availability, you can see now how many mobile phones being utilized in the planet. Okay, so this, we actually make a good reason for the utilization of these cameras as a receiver and say, okay, here is my reason, look into how many cameras are existing in the planet. And then we can use all of this as a receiver from a light source. Again, looking into market point of view, you can see this is a growing industry, and you can see expecting like a huge amount of money that's been pumped into the utilization and manufacturing of these cameras, and specifically here in the CMOS camera, because it's mostly utilized for the smartphone, handheld, and devices. So here is just a summary of annual growth of 10.5%. Okay, here is an example of, if you look into the standardization for this utilization of the camera and what application it was already been, some of them has reported actually in literature. You can see from advertising point of view, you can have a camera, look into a panel light source that can capture a data out of this. You can have an application for, again, is like you can see in a MIMO for providing augmented realities application, where actually camera look into things and showing you differently based on whatever that the information want to be communicated. For again, different security purpose from hazards point of view, you can utilize these for use of actually vehicle to vehicle and automobiles, actually vehicle communication, another way of looking into providing smart cities, smart system, where actually you look more into camera driving you towards your destination without the need of any interference from that point of view. Again, from an application point of view, yeah, you can have from extended reality, you can see this is an application that exists. Again, IKEA, if you're using them, they have an app for that. This is being introduced. Again, tracking localization, another way of looking into things. Okay, I am lost in the city. Where I go, I just hold my phone and it tells me where I am based on a simple capturing this. Another way of communication, enhancing security. Again, for that, you can see my biomedical application where camera can be attached and something looking into depth and basically providing more about vital sensor activity about the human and communicate that to other. You have some research that been done. Again, indoor communication where you actually lack access to GPS and so you or a clone as basically satellite, where you actually need an alternative way to position yourself within building an intelligent transportation system, where we actually highlighted previously. Okay, more about application. You can see now application, you can have an underwater communication. And again, some of this content in AI, and I already mentioned this is content is being created to keep this. Okay, for non-line of sight communications, one of the way of presentation yesterday, again, Vicente was probably looking into some way of this. You can have a light source camera looking at a different place and getting the data out of that. These all are a different way of communication that actually camera can be utilized for and have found its application with. Okay, getting more in details of this, I mean, I use one of the slides that Fari was presenting previously here for the looking in depth of the camera actually is, okay, if I'm getting an image sensor and I'm looking, okay, let's break it down. What do we have in here? And how do we actually, where do we have to look at in order to activate or enable that camera for a communication point of view? So as a common sense, you can have, usually this is camera looking into a lens system as a beginning. You can have a lens in order to focus the light, basically getting more of the magnifying the signal. You get an aperture with a different opening in order to control the amount of the light that is passing into the sensor. This is a common basically aperture available in the market. Moving into the concept of shutter, where actually how does this signal are captured? We have this concept of rolling shutter, global shutter. This is actually the gradual way of capturing the light, depends on a certain exposure time, which is the time that in which that light sensor is exposed to the light. Moving into another ISO is magnification. Okay, it's just it can be a software magnification where how much you want to amplify the signal being captured in order to be able to receive that signal. Moving into quantization, again, this is the way basically the shutter speed and the ISO and the aperture based on the opening of that camera and that gain and the speed of actually capturing that light signal. These are three main parameters that we can actually explore in order to look of how do we enable the use of that camera to receive the data. Again, once the data is captured, you look into the quantization, analog to digital converter, and the way that actually you convert that signal in order to be received in or decoded in the way that we want that is a quantization. Different filtering, that this is one of the filters before the coloring way. You have a RG and a blue one. So debayering filter, you can see is a way of, okay, how do we capture the color from a different perspective? So the sensor will provide that filter, and usually they have all this, and this is the steps and procedure in order to get the different wavelength than this. And we have, again, a gamma correction is another way of actually looking into how I actually correct that signal that being captured and control that lighting in order to ensure the optimal reception of that signal. This can be from a vision point of view as well as from a receiving communication point of view. Okay, moving forward to the communication point of view of that, how do we establish that use of that camera for receiving the data? Okay, we already established having a light source that can be LED, LCD, micro LED, different light of source. You encode the signal and you choose your modulation schemes. You send that, you have an optical channel. You can see we look into a different either spectrum or intensity, and then you transmit that signal over a light source. Here is a rolling shutter as a very, very nice multimedia was actually adopted from here, my previous colleague in Spain, Cristo. He did design very nice way of actually a video of demonstrate, okay, how you can see that flickering of that light with some certain speed. This can be captured, and then based on that capturing of that light, you present the signal and you're decoding it and processing it afterwards. So this is actually how I basically establish that optical communication link in a very simple way and looking into it. So moving forward of that. So here what I'll introduce the project that some of them I did as part of my PhD, some of them moving forward in that and getting in depth of this project from this. Okay, again, AI generated content. I was asking the machine, can you provide me something that can make it more realistic for people to understand? You got a light source, pick up your phone, you can get a signal, whatever you want, you can treat it with a different way of looking into things. Okay, we looked into establishing that data communication. Now, what problem? I mean, if I want to do that, why I'm not seeing it more often? What is the common problem of having these cameras or utilizing these cameras? So basically, we mainly look into the three different problems of having these cameras. Okay, firstly, flickering. If I have light switched in a low frequency, I could be actually causing a lot of problem in a human and health hazards for individual who looked at it. So you can see that light, it flickers. You cannot imagine that having this in a normal, at least some scenarios of indoor, maybe outdoor, maybe it could be at some certain cases you can actually work and having it. But in general way, for a normal lighting system, we cannot afford having a light flickered for a human eye. And this is, I got it from a normal source and looked at it, is this. So flickering is one of the huge, or let's say key factors that is enabling the communication in using optical camera communication. Again, the camera, this has a, you can look into solving that from having high-speed camera where actually you have a slow motion, you can have a lot of data rate, for high frame rate data, you can actually use high switching facility as well as high-speed camera, but this can be, again, daunting, and it was not feasible to everyone. Having that concept of a global shutter, rolling shutter, again, looking into encoding scheme, looking into modulation scheme, this could be one of the solutions that you can actually look into that power of that having a switching and getting rid of it. But we will get more into this at the coming slides. Similarly, from the bandwidth limitation, okay, that exposure of the camera, it will be exposed for a certain time. You can treat it as a low pass filter where actually has a limited bandwidth, because the fact that once you stop that, you actually trade off between the bandwidth and the light that is actually pumped into your camera. So basically, once I expose the light to a certain time, once okay, this is my timing, I'm allowing this power to come in, however, at the cost of having a low pass filter where maybe you get this rigged pulse, it can be a limited bandwidth. This is one of the, actually, I measured the bandwidth of the normal camera, and you can see it's very low. We talk about in a few hundred hertz. Again, another problem of having a blooming effect where actually the light is intense, the camera cannot capture it. Another problem, people might suffer from this, even from a vision point of view. If you pick up your camera, light it into a light source and try to get it, you will have what is so-called blooming effect, where actually then the pixels inside this array will be saturated and you no longer be able to capture the signal correctly. Okay, so now we will have, starting from looking into bandwidth problem and looking into, okay, how do I push that from a point of view from communication? A different way of actually looking into this, we look into color, wavelength, intensity, and the shape of that signal that being transmitted. Here is a way of actually different way that you present and encode your data. So based on that one, you could push a little bit the bandwidth to some level and making it feasible for some certain application. Equalization is another way of actually looking into the problem. Equalization is a pre or post equalization is one of the commonly used technique in wireless communication for mitigating that inter-symbol interference and another problem and pushing the signal forward. Here is some of the literature that actually talk about equalization concept, from having a double equalization, pre and post equalization, to the use of artificial neural network, the current advances in order to enhance the signal, which I work actually throughout my PhD on that, and we will see that in the coming slides. And again, you can have an ANN-based artificial neural network-based decoder. We design a decoder that you can actually enhance the signal and getting back based on the decoding scheme that's been supported by the AI. Okay, here is more in depth of looking into the modeling of that image sensor and having it to sort out and solve the issue of that bandwidth that we have just talked about. Imagine you have a rolling shutter concept is mainly for the rolling shutter, and this each line of that rule exposed to a certain time, it could be in millisecond, and this will lead to, again, to having that rigged pulse, and that will have a basically certain bandwidth limitation. And you can see here is following with the sampling process that to have the quantization that we actually mentioned previously and getting the signal. Here is from a mathematical point of view, okay, how I can get that voltage out of this signal that being transmitted to me. Again, looking into frequency domain of that is just a way of tackling the issue. And then you can see is looking into a problem of, again, having that exposure time will have to sacrifice either a bandwidth or basically the DC gain, the light that comes into the signal. So whenever I get lower band, if I want to push the bandwidth, I have to sacrifice with the gain, meaning that I have to sacrifice with the light that is pumped into that light source and image sensor. I hope that concept is so far is being delivered and everyone is actually getting the idea of this so that we can proceed forward. This is one of my works in that field, okay, using systems. We have an encoding scheme, Manchester encoding schemes to ensure that signal being basically transmitted equally. Each bit you have equal distribution and you get a certain protocol that been designed in order to establish the communication, the data being sent. You can see this is a captured by image, and then it's downsampled and recovered. So that signal here, we got that signal. You can see the signal in here that been recovered with a certain this. So you can see that, okay, this is the more specific about the header, okay, the payload that we designed here. You've got, okay, we measured we look at from a signal to noise ratio from a different perspective in here in the image point of view, in which we actually sum all the rows that represent 1 bit status, and the intensity of each row is accumulated intensity of each row. This will represent the power of that bit or the energy of that bit, and divided that by the signal after getting the DC gain. So we will get, and here we getting this data, okay, to design a equalization using AN. You get the signal, you transmit the signal, you get the signal, and then we do the synchronization and go having a machine and telling the machine, okay, once you get this means that the status is 1 or 0 with some certain training samples, and using this sample actually to train these data. And this is actually more in depth. Okay, you can based on this data, you can train your system and having basically ideal system where you get rid of this rising time and falling time using a simple neural network, a single hidden layer, no deep neural network. It's just a simple one, and you train that and you look into lookup table, getting these equalization, just like nonlinear equalization, where you look into this coefficient and you get that and feed that to a system and use that eventually for recovering the signal and decoding it efficiently. Okay, this is we looked into different basically algorithm in order to train the machine, and okay, which one has offer a best way. You can see a different way of actually different algorithm to train that machine. This paper is already published at IEEE Access. If you want to look into these different algorithms, please welcome to actually look into the signal. Here we look into, again, data rate with and without that equalization. You can see it's failing at very low frequency of low bandwidth. We talk about 4 kilobit per second. You can see the signal is already unable to be recovered. However, within the use of this, you can, in principle, pushing the bandwidth 9 times bigger than itself using this ANN, however, within the limited bandwidth again. Okay, moving forward, dealing with the flickering problem. Okay, just have a look into this. Okay, what we do here, we have a signal. We want to transmit that without the need of having a flickering concept. So how do we tackle this? Okay, we have to say, okay, imagine each symbol will divide into 2 chip size. And the aim is here to equalize the power of this chip. Basically, each symbol has to have a same power level in order to avoid having a flickering. So we divide that chip in the symbol into 2 chips, and it's like, let's say if it is the palm level, and using palm modulation in this specific case, if you have the symbol with the intensity of 3, then add another level of stabilization to get 0. If you have 2, this basically have a 2 chip to compensate for each other. So if you have basically that stabilization unit to get almost the same, so you divide, if it's 1, 0, then you will divide that chip into 2 sides, and you will change the way of looking into that symbol in order to have an equalized power in each symbol. I mean, yeah, I'm not able to see it carefully in here, but you can see in here, okay? You have one symbol that, this is what we called it CP palm, it's constant power palm modulation. So you take a normal signal symbol and you divide that into 2 smaller chips, and you compensate based on that power of the initial one to have equal average power over that symbol. And therefore you tackle the problem of the flickering. And we call that stabilization level, and this is the way of actually looking into it. Again, this is the system that been set up. You have a symbol that you modulate that using palm modulation scheme. You design your protocol, transmit the signal, receive that signal, trying to adopt similarly the ANN equalization and look into the problem without having the problem. And this is the system we design, and it has actually the data, no flickering. It send the data with a few kilobit per second bandwidth, I think 24 kilobit per second. So again, here is just to how do we look into the result? We look from a concept of bit error rate, eye diagram, and this is here I'm just showing the image being captured and cluttered to show the inter-symbol interface that being introduced when I'm using that camera. You can see moving transmitted from 200 Hz up to 1.5 kilohertz, the data units. You can see the recovery of that signal is impossible without the equalization. However, within the use of equalization, you can see we are able to actually recover the signal, and here is the maintaining that the data rate required. So yes, we did look into this, we established this, we look in the results from eye diagram, linearity and error rate performance point of view. And again, the paper here is published and you can access that online. Okay, getting it from this to this one. And if you notice, you have 1, 2, 3, 4, 5 layers. In principle, we have 4 PAM, yeah? PAM is 4 level, but here you will see 5 because we designed actually the header in order to look in the beginning of that symbol with another level, and that we used for utilizing the signal and recovering it. Okay, this is from data communication point of view. Okay, moving forward, another application for that camera from localization point of view. Okay, again, from a concept of having the use of this camera for localization, mainly for indoor. I guess here from a tunnel point of view, we heard a lot about Chile and the use of that in here. Okay, camera can be utilized for that from advertising. This is, I put a multimedia from my previous project that we worked with Fari and another company based in the US. I guess we developed a system where you actually trying to, for localization, mainly for maybe can be for advertisement of some application. You can see that camera can look into things, position the things, and using this for some certain purposes. Okay, this is the website of that company anyway. So from that concept, moving to the, let's look into, okay, what we can do from a localization point of view. I will brief here of, okay, what we have done from a localization. So using a single light, we say, okay, using a single light that been sent on a camera receiver, you could in principle work out the position and telling you where you are in that based on a specific algorithm that you can develop. So here is our scenario that we put forward for that. Again, you have a light source sending its ID, and the ID is modulated and sending it through a light source, flicker-free light source for sure. Again, the signal is being received in here. You get a camera, and we did some processing in here in order basically to work out the position of that light source in the image and working out the position out of that. I will not go in depth into this, but we'll see the following slide a little bit of these details of how did we mention this. Here is the system parameter that been adopted from a current bias current that been used for the lighting the LED. Again, from the camera receiver point of view, what is the parameter of the receiver, then the channel up to basically 2 meters, and then we used how to evaluate the positioning. We use a specific robotic arm with a high resolution in order to be able to measure accurately the positioning. Here is actually the system experimental setup that we've done. You get a camera, the light source sending, we move that along the certain basically room size in indoor with some certain exposure. And you can see here we test different exposure time, and in order to detect in the camera basically that light source and what is that from term of accuracy, how accurate is this locating that this. So this is a photograph of the setup. Moving forward, different exposure, you can see from having a light source like this captured in a camera to having intensity one and a blooming impact that actually impact the accuracy of that signal. And here is, if you take that one and we just look at it carefully and saying, okay, what is the minimum, what is the maximum for a different one? You can see this is a rainbow just to show the procedural increment of that exposure over time, basically. And here is the detection of that light source from a different exposure. And we looked into something called peak signal to noise ratio, is the pixel signal to noise ratio based in transmitted receive one, and find the difference. Again, this paper is already published and you can find the source in here. Yeah, here is another technique that we used in order to tackle that problem of having these different exposure and a blooming impact. Okay, if I'm using a small impact, I can locate the source. If I have a high power exposure for the camera, you can see that location of that source in the image. It might be a bit of difficult way. So we introduced something called mask generation, and it's just like, okay, detect that initial size or radius of that one and generate a one, and then do multiplication between both of them, and then give me the signal. And let's look into what difference in terms of exposure time. And you can see here is normalized received one over that pixel. And you can see, you do that way of doing this, so you can actually get the same result of accuracy along the way, and meaning that I'm trying to localize the center of that light based on this technique, and rather than having exposure. So sort of you solve the problem of having different exposure time. Oh, sorry. So I'll go forward in that. Sorry for this. Again, from a localization point of view, this one I will be presenting it in my presentation as a paper that I worked with Vicente. Moving forward okay, I'll just go through it fast. I will not talk about it. Sorry, because I will talk it later, because this, from a physical point of view, security, you can have you can use the camera. You can see a lot of camera used for security purpose, that you have it in everywhere. So you can utilize that to provide a security region. You can have a light source moving forward, and you design a system. Again, if you are interested, we can talk about this later on. And this was a collaboration with NICT. The last bit of this is more about introducing Carlos' work and myself about a single photodiode that you can have from a point of view of having optical receiver and a single photo cell. So we were looking into a photovoltaic. It says, can we use this as a receiver? Can we capture that? And having a self-powered receiver that can actually capture the signal, as well as providing basically energy harvesting without the need of power source. And this is one of the samples that we actually gather from in collaboration with the Finland Institute and Oxford. They fabricate the samples for us, and we use a material called perovskite, and that has an ability to self-powered, and it provides basically more efficient than silicon. This is a very new result of the work. It offers a wide absorption and offer flexibility as compared with normal photodiode. This is from a design point of view. We will see that work about from a communication point of view. So we took that sample, trying to actually look at it from a point of view, can we use that as an optical receiver? And if we, how do we actually characterize it? So here is it. I'm just going very fast about this. Okay, as simple as that, looking into this, that perovskite material, it has three different actually elements from the perovskite material. And from a chemical point of view, we get the electron and hole transport layer. We use some basically different materials for design than being actually suggested to be used, some of them to allow the transport layer for electron to having a fast transportation for that electron, and delivery for the again for the holes. Here is like the electrode. In order to have a high conductive electrode, you use the gold for that. You can see with because it has a higher conductivity and excellent conductivity. So looking from this point of view, we assemble the assembled one. We look from energy and communication characteristics. I mean, the characterization from optical point of view will later on, just after me, Carlos will present that to some level. And before I actually conclude here, I'm just getting this opportunity to play this multimedia for the other project that we work with in Northumbria with. And that was basically trying to establish the use of optics in the space. If you are, please, can you open that multimedia for 2 seconds? If you play the multimedia, and this is just to show a brief introduction, then we can conclude. So this is one of the latest work that we are doing at the moment. So basically designing that CubeSat for the use of space. The project was funded by the UK Space Agency, and this is so the aim is to actually create a communication between inter-satellite communication link in the space. Here you can see with some certain distance with 1,000 kilometers, with some collaboration with the different universities and around in the UK basically, and with the companies trying to design that one. So basically, we started the optic communication here from a computer point of view, also at a company leading for the computational power of that one. In Northumbria, we're trying to establish the optics links, as well as we have a team for the solar cell. Here is with the Durham, they're trying to design the optics that been enables for us to do for a communication point of view. So we talk about the aim is to having gigabit per second data communication and creating an inter-satellite optical link between two of them. And this is a simple video that actually developed for a marketing point of view, and just to show the concept. Again, if I'm just moving to summarize from that point of view, trying to have 6 CubeSats, basically very small one, INTES, and having high data rate. And basically this is where sit in the, based on whatever exists in the literature. And here is the head or optical, the initial design that we worked out. And yeah, I will be further in this work. We are currently working on that, and hopefully we'll reach somewhere and report the result eventually after this. So again, just to summarize the work for OCIG, because I'm a part of the optical wireless, as I said initially, I just put some of the word and what has been developed by, actually led by Fari. You can see him in here and here as well. And here is some of the work of the camera that we look. Here is for a communication that previously, and this is my colleague Shishang again developing this. And this is the CubeSat, the previous one, initial demonstration in the lab for that one. I mean, to conclude the things, okay, this is what we looked at. We looked at the OCC as a way of communication and compared that from DLC. And basically, this is the funding that OCIG and FARI has obtained over the years. And I'm actually glad to be working as a part of it, as well as the new that. And here is the thankful for everyone who listening here. And I'm happy to actually, and sorry for the latency, and I'm happy to have a new question and anyone have any concern in that regard. Thank you.
Thank you, Othman, for your presentation. Very interesting. Questions? Anyone?
Very, very interesting. Yeah,
Thanks,
I really
Ishan.
like your work and also your presentation. Congratulations for achieving all of that. I know it involves a lot of hard work, and I can see from you. Yeah,
Thank you so much, Ishan.
yeah, so I'm really happy with your progress. And so, Atman, the CubeSat is a very interesting project, you know. So what do you think could be the challenges? Maybe the data rate is okay, you can achieve with commercial lasers. Do you think that, what's the challenge you think that could be?
Okay, thank you, Ijaz, for the question. Actually, very good question. Okay, having a CubeSat and enabling this. Okay, what is the challenges of establishing CubeSat based on optics communication is we look from actually few problem and key point. One of the main key point is actually having the ability to track that signal from acquisition and tracking point of view. So basically having a path model of positioning, acquisition, and tracking is one of the main challenges, where you actually you have two dynamic systems moving independently, and you want to locate one source to another, and basically trying to find the area and in which that you exist, and then look into a very small and tiny, we talk about few micron, like 20 or 100 micron photodiode or photodetector. And this is one of the key challenges for enable such a system. And for the knowledge of people, there is no existing path in the space at the moment in the planet at all. So one of the key challenges for this project is having a path system, basically locating that light that being transmit to the receiver. And another key challenge, actually having the data communication, it's also very challenging regardless of the laser, because the fact that you end up you want to have a smaller system with an optics that have been designed to transmit that signal, and again, it has to have a high speed and low latency, and having the optics that can survive in the space is another different problem. And third of all, actually having the problem to deal with the space, once you go to space, everything changed, because the fact that you have to look into temperature point of view, a different characteristics altogether. You want to survive for long, you want to survive a high temperature, low temperature, and you want to be as power efficient as possible because you want to last long. So you have to come up with a solution for this. This is a very new to me and very challenging. I mean, I'm always trying to refer to Pari and people from physics to help us with this. I mean, we have now a new lab that even Pari and Eamon and then Robert Weeks is as well, like they started and trying to basically moving the direction towards that, because it's a growing industry. You can see a lot of big companies now trying to do such a things. And I mean, SpaceX, for example.
So I've been looking on satellite communication toolbox on MATLAB yesterday.
Yes.
It's for radio communications, but I think it's very paramount that you simulate your system really, because once you're in the space, so maybe my question is, are you simulating? Is there any platform you can use to simulate?
I mean, having to simulate the system is also another challenging factor to establish high power intensity, and you want to be having a reliable one. So yes, we are trying to work out, we have a plan to do a testing, and basically we have from a simulating point of view, we did already budget analysis in MATLAB and so on. But from an implementation point of view, you have a totally different domain. You come up, we have a lot of support from industry and trying to solve that problem, but having this is again a challenging thing to look at.
Thank you so much.
You're welcome. You just hope to have that list.
More questions? Okay.
Thank you. I enjoy your presentation. Many different ideas.
You're welcome. Thanks.
It's hard to follow all of them. Very much. So I have a question regarding. This is the first time I read a few things about camera communications, but I find it very interesting, and many challenges we need to find and solve. Regarding the pointing of the camera from a mobile phone, is that an issue? Is something that you take into account for the test you've done so far?
Yes, thank you for the question. So looking into the camera point of view, so what we deal is we have what's so-called field of view, which is the angle in which the camera can actually have access to. It's like the example of yesterday, Fari was mentioning, okay, and if I'm in a room and I'm opening my camera, how many light source will I see? Basically, it depends on the field of view of that camera. Changing that field of view will change the amount of data captured per frame. You know, imagine have a picture or a frame, and if I'm decreasing that field of view, I'm actually changing the data rate. I'm changing the amount of data being transmitted and received per a single frame. And therefore, yes, it does play a role. And we have actually worked out an equation is already, if you look into literature, you will find it. And basically, okay, in increasing that will have some certain amount of impact in terms of how much data I can send per a single frame, and therefore for a multiple frame, and then eventually working out the bandwidth or data rate. Thank you. I hope that it addressed your question.
And I have one more question, if that's all right.
Yes, sure.
Obviously, the data rate is limited, and you would like to find some way of increasing the dimensionality of the data we see. But you have your camera has just an intensity. So is there any chance that we could build now a camera phones, cameras that have sensitivity for polarization? Maintaining intensity, but if we added polarization, then maybe we could have some extra dimensionality for it.
I think this is a very good question as well. I mean, there are actually some of the people who looked into having a camera in which that array, you know, that pixel array, one of them used for visionary and the other for the data, in which you provide that high data rate. And this was reported in Japan, and they have achieved around 100 meg based on initial design. But okay, why I'm looking here from a different perspective is because we are trying to access whatever existence in literature. So I mean, looking from that perspective, I think is very futuristic and it's very nice. And I think probably, yes, it depends on this manufacturer of these CMOS cameras, and maybe they come up with this. and they adopt that scenario, and in which you have both of them and you will enable higher speed. But yeah, that's my answer for that. Thank you.
More questions?
Okay, thank you. Congratulations for your presentations.
Thank you.
I didn't see it at all, but I would like to know if it is possible for you to provide us a little bit more details on the advantage on perovskite, not only regarding to bandwidth enhancement, but also in terms of energy harvesting.
Okay, so thank you for the question. A very nice question again. For that, from an energy harvesting point of view, because we characterized that one as a part of one of the paper that Carlos was leading and myself as a part of it. We looked into this characterization from a PV point of view, from energy harvesting, and we measured efficiency for that one. And I didn't want to get into details because right after me, he will go and in the stage and he will show you exactly what you were asking for, and hopefully will address your concern from that point of view. I hope that's okay for you. Yeah.
That's okay, it's okay.
Thank you very much.
You're welcome. Thanks all. And thank you.
Now we start with